So, after finding the electric potential and the electric field for a system of n number of charges, for a single charge and for the dipole, let us find out the relation between the electric field and the potential. So we are considering a source charge at position O and we are having a test charge at some position A. Now, because of that source charge, electric field is acting along the right side, that is E vector, and the potential at VA at A position is VA, that is equals to V. And as we are displacing this charge from position A to position B through a displacement dr, then there is increase in potential as we are doing work against the repulsive force of this source charge. So the final potential at position B is V plus dV. Now, here are the quantities. E remains constant for the point A and B because these points are almost very close to each other. Now, force required to move the test charge Q naught against the force of this charge plus Q is given by F is equals to minus Q naught E. The negative sign shows that we are applying the force against the electric field. So mark it as equation number 1. Now the work done to move the test charge, because we need to find out the electric potential. So the work done will be force into displacement, and the force is F and displacement is dr. So the work done is F dr. Substituting the value of F, we are having the work done is equals to minus Q naught E dr. Mark it as equation number 2. Also we know that the work done in moving the test charge in the form of potential is given by W is equals to Q naught VB minus VA. And we know that the potential is work done per unit charge. Substituting the value, we are having work done is equals to Q naught dV, where dV is the change in potential, that is the potential difference between position A and position B. Now this is also work done, this is also work done for the same thing. So let us equate these equation 2 and 3. After equating these equation, we get minus Q naught E dr is equals to Q naught dV, or Q naught cancel out. We are having E is equals to minus dV by dr, and this quantity is known as the potential gradient. And this negative sign shows that E is acting along the direction of decreasing potential. Why we are saying the decreasing potential? Because in this figure you can see that this is the potential for the outer point, this is the potential for the inner point. Now we are doing work against the repulsive force. So in order to make this charge to move from this position to this, we need to do work against that field. So the field is always opposite to the direction of increasing potential. Okay, so E is equals to minus dV by dr, and we'll use this relation E is equals to minus dV by dr in your potentiometer as well. Okay students, so after this our next topic is calculation of electric potential from electric field. Now we had established a relation between electric field and the electric potential. Now using that relation, we will find out the electric field formula for the electric potential using that electric field for a given charge system. Now E is equals to minus dV by dr, and using this we are having dV is equals to minus E dot dr. This is the dot product of two quantities, and the dot product shows that this potential is a scalar quantity. Now integrating between the limits r1 and r2. Here there are two variable quantities. On right side this is the position of the source test charge and this is the potential respective to that position. So integrating with the limits, we are having integration of dV from V1 to V2 is equals to integration of EdR from R1 to R2. Now solving this left hand side, upper limit minus lower limit for the variable is equals to minus integration of EdR from limit R1 to R2. So these limits are for the finite position. What if we are considering that we are displacing the test charge from position infinity? So in that case, if R1 is at infinity, in that case potential at that position will be 0. And we are taking R2 as the final position, that is R. Then the potential at R will be V R vector. Hence substituting the values in this relation and we are getting V vector R is equals to minus integration of E dr from limit infinity to R. Okay. Now there is important point to remember that the electric field is having two SI unit. One SI unit is your volt per meter and another one is Newton per coulomb. This is from the formula F is equals to QE and this is from the formula E is equals to dV by dr. And let us show that these two relations or units are equivalent to each other. The SI unit for electric field is volt per meter. Volt is potential, that is work done per unit charge, that is joule per coulomb. And again joule is what? Work done is force into displacement. And substituting the values, we are getting Newton meter, coulomb meter. Meter cancel out and we are getting volt per meter is equals to Newton per coulomb. Okay, so this is the relation between volt per meter and Newton per coulomb. After this, our next numerical is a uniform electric field of 30 Newton per coulomb exists along the x-axis. Calculate the potential difference VB minus VA between the points A, 4 meter, 2 meter, x and y coordinate, B, 10 meter, 5 meter, again x and y, abscissa and ordinate. So we know that in order to solve this, E is equals to minus dV by dr, or the change in potential, that is the potential difference, is equals to minus E dot dr. Now the position is only varying along the x-axis. Therefore, change in potential is equals to minus E delta x, and that is equals to minus E x2 minus x1, that is this is x2 and this is x1. And after solving this, we are getting the change in potential, that is the potential difference for two different positions on x-axis is minus 180 volt. Our second numerical problem is the electric field E is given as 20 I cap plus 30 j cap Newton per coulomb. Here electric field is given in vector form. It exists in free space if the potential at the origin is taken 0. Find the potential at position 2 meter and 2 meter, that is for x and y positions. Now we know that E is equals to dV by dr, or dV, that is change in potential, is equals to field into the change in positions. So here the change in position for the x-axis, change in position for the y-axis, and substituting the values, E along x-axis is 20, E along y-axis is 30, and 2 is for x and 2 is for y. Substituting the value, and we are getting the potential difference as minus 100 volt. So students, there are two numerical problems for your practice. Find the electric field between two metal plates 3 millimeter apart connected to 12 volt battery. Here the given quantities are the potential and the distance. You need to find out electric field. Again, the formula for electric field is dV into dr. So this is potential V, this is dr. You need to change 3 millimeter into meter, that is SI unit, and you get the result. Our next numerical problem is a uniform electric field of 20 Newton per Coulomb exists in the vertically downward direction. Find the increase in the electric potential as one goes up through the height of 50 centimeter. Again, field is given and the distance is given. Convert this in meter and you will find out the potential for this particular condition. So we had find out the relation between the electric field and the potential. Then we calculated potential from the electric field. Now our next topic is equipotential surfaces and their properties. As the name suggests, equipotential means the potential is equal for these surfaces. Hence the name is equipotential. So what is the definition for the equipotential surfaces? Any surface that has same electric potential at every point on it is called the equipotential surface. So for a given surface, the potential remains constant throughout that particular surface. Now what are the properties? The work done is zero, because let us consider that this is a equipotential surface and we are having 2 points, A point and B point, separated by some distance. And this is the direction of electric field that is perpendicular to this surface. Now if we want to displace this charge from position A to position B, that is through the distance dl, in that case the work done is 0. It means these 2 points exist on the same potential. Hence we are saying that this is the equipotential surface. So work done in moving a test charge over equipotential surface is 0. Second property is electric field is always normal to the equipotential at every point. And as we know that electric field is always perpendicular to the surface for a given conductor. Third point, equipotential surfaces are closer together in the region of strong field and farther apart in the region of the weak field. This is just as like the electric field line. The electric field lines are close to each other near the strong field and the electric field lines are far apart. And as we know that E is equals to minus dV by dr, or the displacement will be minus dV by E. So from here what we are concluding, that as the distance is proportional to 1 upon electric field. If it means if electric field is increasing, the distance is decreasing. So the field lines are closer for increasing electric field. Okay. So from this what we are concluding, for constant change, if change is constant, that is if E and R are changing at constant pace, in that case V is constant. And you can see figure out this thing as we are having concentric circles. For a given circle, at any point on the circumference, the potential remains constant. So this is how the equipotential surfaces look like. Fourth point is no two equipotential can intersect each other. What if the equipotential surfaces intersect each other? again they are showing that the potential at the 2 points will be will be some given quantity, and we know that the potential on the equipotential surface, that is the potential difference, is 0. But if they cancel out each other, we will get the two directions respective to these two equipotential surface for the electric field, and which is not possible. At a given point, we are having just one direction for the electric field. Hence, no two equipotential surfaces can intersect each other. After the definition and the properties, let us see how the equipotential surfaces look like. So these are some equipotential surfaces for various charge systems, and we are having number 1, the equipotential surface for a positive point charge. We are having a positive point charge. We can take a negative point charge as well. So the basic difference between the positive and negative point charges are the field lines are away from the point of positive charge and the field lines are towards the negative charge. Now you can see from this figure there are concentric circles for this positive charge, these. So these are the equipotential surfaces. These lines represents the electric field. These are the lines of force, and these surfaces are equipotential surface. So if we are displacing the charge from this position to this position on this circle to this position or to this position, the work done will be 0 because the potential is equal for this circle at any point of this circle for this particular source charge. Similarly, for this circle, again the potential will be same at any point with respect to this charge, and so on. So these are all represents the equipotential surfaces. Now V remains constant for R constant, as we had find out this in previous topic. So as the distance of this circle from this center is constant at any position, so V is constant for next, and so on. Now the next is equipotential surface of two equal and opposite point charges. Now in this case, we are considering a dipole. Now we are having a positive charge, we are having a negative charge, and they are forming a dipole. And here are the electric field lines, that is the lines of force, originating from positive charge, terminating at negative charge. Now what we are observing here, the field or the potential surfaces are closer to each other near the dipole, that is inside the dipole, but they are far apart from each other outside the dipole. So what we are concluding from this, that this is the figure for the equipotential surfaces, and this shows that the potential vary here. The potential is more for these outer point and the potential is less for the inner point in case of the dipole system. But in case when we are considering equipotential surface for two equal positive charge, what we are getting this, that the equipotential surfaces are closer to each other at the other side of the charges, and in the repulsive region the equipotential surfaces are far apart. Means in order to bring this positive charge close to this, we need to apply more potential. That's why the potential is increasing over here. The next case is equipotential surface for a uniform electric field, that is we are having the equipotential surface for a uniform electric field. As the field is allowing this direction, we are drawing the Gaussian surface for the flow of the electric field, and what we are getting, that the potential remains constant for this uniform electric field. Now after calculating the equipotential surfaces and understanding the concept, and after the potential difference, let us find out what is the energy associated with a potential. So our next topic is electric potential energy. And what is this electric potential energy, because when we are displacing one charge from one position to another position, we need to do some work. Okay, and when we are doing some work, we need some energy. So amount of work done in assembling the charges at their location by bringing them in from infinity is the electric potential energy. So here we are having charge Q2, which is at position somewhere at infinity. We bring this charge from infinity to position B. Okay, so we need to do some work in order to bring this charge from infinity to position B. Now this final position of this charge Q2 is at a distance R12 from the charge Q1, which is at position A. Okay, so this charge Q1 is at rest, so the work done on this charge will be 0 because we are not doing anything in bringing this charge from any position to any position. As it is at rest, so it remains at position A. So the work done associated with charge Q1 is 0. Mark it as equation number 1. But we need to do some work for that charge Q2. So the electric potential due to charge Q1 at point B at distance R12 from A will be, now the potential at Q1 due to Q2 will be V1 is equals to 1 upon 4 pi epsilon naught Q1 by R12. This is Q1 charge and separation is this. Now if Q2 charges move from infinity, so work done will be what? Potential into charge. And what is the potential at this point due to this Q1? This is V1 into Q2. And that is 1 upon 4 pi epsilon naught Q1 Q2 upon R12. So we need to do work in order to overcome this potential. As the work done is stored as potential energy. We know that work done is stored as potential energy. So let U be the potential energy for the system, that is for charge Q1 and Q2. They make a system. So for this system, the work done will be work done for charge Q1 and work done for charge Q2. But W1 is equals to 0. So substituting the value of W2, we will find out the net electric potential energy for this displacement will be 1 upon 4 pi epsilon naught Q1 Q2 upon R12. Okay. After the system of two charges, let us find out the work done for the system of three charges, and the potential energy will be the net work done for the system of three charges. So our next topic is potential energy of a system of 3-point charges. Again, from this figure you can see that we are having three charges at position A, B and C. Charges are Q1, Q2 and Q3. For this system, for this we had already calculated a relation for the potential. Now there is another charge which is entering this system. Now what happens when we are bringing this charge from infinity to the position C? We need to do some work, and the work done will be against the forces of Q1 and Q2. So the work done on charge Q3 will be W3 is equals to potential at point C due to Q1 and Q2 and Q3. Now the work done will be 1 upon 4 pi epsilon naught Q1, and the separation of Q1 from Q3 is R13, and due to Q2, that is 1 upon 4 pi epsilon naught Q2, and the separation is R23. Substituting the values and multiplying this with the charge, because work done is potential into charge. So the work is done on charge Q3, and that is equals to 1 upon 4 pi epsilon naught Q1 Q3 upon R13 plus Q2 Q3 upon R2 3. Now the total electric potential energy for the system will be what? That is the work done on charge Q1, the work done on charge Q2 and the work done on charge Q3. As we had discussed earlier that work done on charge Q1 will be 0 because the Q1 charge is at rest, and for W2 we had already calculated, that is Q1 Q2 upon R12, and W3 is this value. So let us all these three quantities, and what we are getting, the total electric potential energy for the charge or for this 3 charge system is 1 upon 4 pi epsilon naught Q1 Q2 upon R12 plus Q1 Q3 upon R13 plus Q2 Q3 upon R2 3. So the potential energy of system of n number of charges can be written as, here what we are seeing that there are variable quantities. So we'll take two variables I and j in order to define the relation. The net potential energy for n system of charges will be U is equals to 1 upon 4 pi epsilon naught summation for all the pairs Qi and Qj divided by their separation Rij, and that is equals to 1 by 2 1 upon 4 pi epsilon naught summation I is equals to 1 to n summation j is equals to 1 to n, but the condition is I is not equals to j, Qi Qj upon Rij. So why we are adding this factor 1 by 2? Because we are having pair Q1 Q2 by R12. We'll also get another one Q2 Q1 by R21, and both are same thing. Similarly, Q1 Q3 by R13 is equals to Q3 Q1 by R31, and both are same. That's why when we are adding these two, we are taking the half. Now the points to be remembered for this electrical potential energy are: number 1, the potential energy of two like charges, that is Q1 and Q2. In that case, Q1 Q2 product will be greater than 0. In that case, the electric potential energy is positive. But on the other hand, the potential energy for two unlike charges will be negative. Okay, students? So after this, what if this system is experiencing some external field instead of the field of these two charges or the source charge? So in that case, the potential energy in an external field is given by, we know that potential of a charge in external field is equals to charge into electric potential, external potential. So we can say that the potential energy is equals to potential divided by the charge, or electric potential at a point will be potential energy of unit positive charge at that point. Now let us find out this potential energy in case of a system of dipole. So we are having a dipole. Again we are having electric field lines, and E shows the direction of electric field lines. This is your dipole, minus Q plus Q charge, forces plus QE and minus QE are acting opposite to each other. The length of dipole is 2a, and this dipole is again making an angle with the electric field lines. Now we had already calculated that there is a couple acting on this dipole and which exert a torque. Now the couple exerted by the torque is given by, the torque is QE 2a sine theta, because what is torque? Torque is force into perpendicular distance. Force is Q into E and the perpendicular distance is 2a sine theta. Also Q into 2a is the dipole moment. Substituting the value, torque is equals to PE sine theta. Now a small amount of work is to be done in order to displace this torque through an angle theta. So the small amount of work done in rotating this dipole through an angle d theta will be, work done is force into displacement or torque into the perpendicular distance or the displacement, and we are having the torque, work done is torque into displacement, And what is torque? Torque is P is sine theta. Substituting the value, P is sine theta d theta. Now, this is the displacement through a small angle d theta. What if we are rotating this dipole from theta 1 to theta 2? In that case, the total work done will be integration for this small amount of work done, that is for small angle, and substituting the value, we are having the total work done is equals to integration theta 1 to theta 2 Pe sine theta d theta, and this is equals to Pe after solving this minus cos theta, theta 1 to theta 2. And students, we know that integration of sine theta is minus cos theta. So applying the limits for theta, that is cos theta 1 minus cos theta 2. And what we are having, the final potential energy, that is the amount of work done. As we know that potential energy is stored as the work done. So we are having Pe cos theta 1 minus cos theta 2. This is required potential energy. And if we are considering the positions, theta 1 is at 90 degree and the final position of theta 2 is theta. In that case, substituting the values, and we are getting a relation for the electric potential as minus P dot E, because cos theta is there, so this is the dot product. So this is minus Pe, and why we are taking the negative sign? Because we are displacing, or we are applying the potential in order to displace the dipole against the direction of electric field, or we can say that the dipole moment always act opposite to the direction of electric field. After this, we are having this relation. Now there are some special cases associated with this. What is the position for the stable equilibrium? When the dipole is in equilibrium, stable equilibrium, when theta is 0 degree, in that case we are having the potential energy is equals to minus Pe cos 0, that is Pe. So P is minimum for the condition when the dipole moment and the field are parallel to each other. Second case, the position of unstable equilibrium, when we are rotating the dipole through 180 degree, then the potential energy will be minus Pe cos 180 degree, and Pe is maximum. So potential energy is maximum here. So potential energy is maximum for the case when the dipole moment and field are anti-parallel to each other. And the third condition is the position of zero energy. When the theta is 90 degree, the potential energy is minus Pe cos 90 degree, and that is 0, because cos 90 is 0. So work done on any charge, here we are considering plus q, is equal to the work done on minus q. So we are saying that the work done on both the charges are same, but they are in opposite direction, hence the total work done will be 0. Now students, we are having a numerical problem in order to solve some questions based on this electric potential, potential energy. And so the first numerical is 3 charges minus q, plus q and minus q are placed at equal distance on straight line. If the potential energy of the system of 3 charges is 0, find the ratio q by q, capital Q by small q. So this is the figure, these are the positions for the 3 charges. Potential energy of the system is 0. This is given in the numerical. Therefore, adding the potential energy for all the charges, the energy on this because of these two, this because of these two, and this because of these two, superimposing, we are getting the net potential energy is 1 upon 4 pi epsilon naught minus q upon r, distance between the charges, q के बीच में distance, that is 2r, here q and minus q again r, and what we are getting, that this is equals to 0. This is the condition given in numerical. So after solving this, we are getting a relation q by q is equals to 1:4. And students, there is another numerical problem for your practice. 2 point charges A and B of values. Values are given, distance is given. You need to find out the work done and apply the relation, and you will get the result for this numerical problem.